Okay. So, hello everybody. Welcome to today's talk. Our speaker today is Karen Seidel from University of Potsdam, talking about modeling binary classification with computability theory. Please, Karen.
Yes, so thank you very much, Katarina, for the chance to present my work here. So the talk will give an outline of what I did in my PhD. And as I have 50 minutes, I will also try to go a bit more into the details or some basic ideas of the proofs. I hope that I will meet the time, so I'm not used to 50 minutes, so please forgive me if I'm not perfectly on time. But yeah, so what I was concerned with was modeling learning, for example, binary classification with tools from computability theory. Machine learning is in our everyday lives everywhere, and gains motivation from research also in learning. And also there is the origin of inductive inference, the area that my PhD is located in. And there are very fundamental and abstract models that are that can be tackled with the instruments from mathematics, and they provide insights that help the practitioners and engineers that, for example, program and develop machine learning algorithms to design them and to know maybe what is a good approach and what is maybe not so promising. Yeah, so in email classification, as an example, one has a lot of properties called features of the email. For example, the age of the sender and the IP address. And what the algorithm is supposed to do is it is supposed to output some classifier that for an unseen email tells tells whether it is a spam email or not. Okay, so as an example, we have one specific user that labels the emails that come in as spam or does not, and now our algorithm first sees, for example, a non-spam email, and it will output some classifier. Let's just assume that it outputs linear classifiers, which are still very much used. And after having seen another email that is labeled as spam, it sticks to this classifier that will label every email with features on the right of this half space as spam. And it goes on until it sees, for example, a third email, and this third email is labeled also as spam, but would not have been labeled this way by the classifier that was suggested in the second stage. So it changes the classifier that it outputs, for example, to this one, and this goes on and on. And in the end, at each time step, the algorithm will have seen a certain finite amount of data. It outputs a classifier, and what we want is we want some classifier that is optimal in the end, and this means in our setting that it is 100% correct, and also that it is eventually correct, so that at some point time t it will be a correct classifier. Okay, so we talked about half spaces that are a valid hypothesis, and this process is a so-called conservative process, because conservativeness means is defined to say that the classifier is only changed if there is a reason to do so. So if there was an email received that contradicts the last output classifier. Okay, so there are many properties that one can pose as additional properties. The one I talked about on the last slide was conservativeness. Another one that is related and originates in cognitive science research on the learning behavior of children, for example, when learning languages or learning mathematical concepts, is the so-called U-shaped learning. And the U-shaped learning process is a learning process in which the child, in this case, first shows the behavior that one would expect. So, for example, if for irregular verbs in English, it would use the irregular term. And later on, it will, for example, if it used broke correctly, it will use braked. And later, when it grows older again, it will use the irregular form broke again. Okay, so this has been observed and is modeled also in our setting. And there are basically two definitions that are common. The first one I want to mention is so-called non-U-shapedness, meaning that the optimal classifier is not withdrawn. So what we want is we want to find out whether we can learn still as much when we forbid this kind of behavior. And and so this is the first definition that was analyzed, and the second definition that was analyzed is so-called strongly non-U-shaped learning. And this says that not only the classifier is not withdrawn, but also the program for the classifier is not withdrawn. So in the first definition, the algorithm would be allowed to output another hypothesis that stands for the same half space, but maybe is encoded differently. And in the second case, even this, the parameters are not allowed to be changed that are output. Okay, so one could first observe that that a conservative learning process is also non-U-shaped, because once the optimal classifier is output, it will never be inconsistent again. So there is no need to revise the hypothesis. So what we do in inductive inference is we look at recursively enumerable sets as our hypothesis. So we do not restrict ourselves to half spaces. And one way to look at it is to say that every email in this very high dimensional space, I only drew 2 dimensions here, every email encoded as its feature vector represents or can be encoded in a natural number. And then, what we want to learn, so this specific email classifier for the person is given by a code for or a grammar that enumerates all the spam emails. Okay, so this is what we want to learn. So the very general hypothesis space that is very often considered is the so-called W hypothesis space, which is the collection of all recursively enumerable sets. And and so at some time t, we want to output some hypothesis ht that stands for this grammar. Okay, so now again, to visualize the learning process, we start with some initial hypothesis without any information. So the learning algorithm has some initial hypothesis, and there has to be some time t0 such that from t0 on, the algorithm is correct, the classifier output is correct. Okay, and now there might be other hypotheses in between, and we investigate whether the learning process, so the process or the sequence of classifiers output, has certain properties. And for example, this would not be conservative. So the example I showed you with the half spaces was a conservative learning process in which always the next or easiest half space that fitted the data was output. But here in this example, the third email seen is consistent with the second hypothesis, and still the learning algorithm revises its classifier. And one question we looked at is this necessary? So yeah, can we find collections of languages? So yeah, for example, I mean, the example I talked about was the collection of all personalized spam classifiers, and there are more general collections. And the question is, can we find such a collection of languages that is learnable in general, but not in a conservative way? And what we showed is that the answer is no for this model. So when learning from positive and negatively labeled data, this is not the case. Okay, so the general idea, and I will go a bit more into detail later, is of course we want to construct an algorithm that, like, if we assume we have a successful algorithm, we want to construct another one that learns at least the same concept, so at least the same collection of languages, but does this conservatively. And there we prove some lemmas. So one is that that it is enough to consider the canonical presentation. So far this is an adversarial model, and the learning algorithm has to succeed no matter how the data, in which order it is presented, and it may contain repetitions and so on. But yeah, we showed that this is not a problem for the conservativeness. And also we showed that we can assume that the learning algorithm always terminates, so always outputs some classifier. And also that no classifier that was already guessed is repeated. Okay, so we showed this by thinning out the hypothesis appropriately. So this is now conservative, but there are other properties that we are looking at, like next to also non-U-shapedness. One is strong monotonicity, which says that that we only guess greater sets. So we only, in going back to our example with the spam emails, only larger sets of guessed, or yeah. So the set of spam emails can only grow during the learning process. This is what strong monotonicity requires. And as this is not the case, going from H0 to H1, yeah, so we do not have a strong monotonicity here. And indeed, we will see soon that that this is also a restrictive assumption in contrast to conservativeness. Another important criterion is cautiousness, requiring that the algorithm does not go back to strict subsets of its recent guesses. And monotonic learning is very similar to strong monotonic learning, with the difference that that we only require the superset relation with respect to the intersection with the language or the concept that we want to learn. Okay, so one important example that separates monotonicity from cautiousness are the cofinite sets. So the collection of all complements of finite sets. And the strategy that also works here very well is, again, Occam's razor-like strategy, saying that that you guess that the negative information you have seen so far is all the negative information there is. And as there is a finite amount of these negative information, you know that once you have seen all the negative information, you will have succeeded. And on the other hand, one can show that this is not a cautiously learnable simply by, so this is a very typical argument, a locking sequence argument, by saying that when I have guessed the whole set, or yeah, so the whole set of natural numbers is an element of this collection. And as the learning algorithm has to be correct on it, I know that, that there is a sequence after which it will be correct unless it sees some inconsistent data and will also not change its mind. So I'm presenting this locking sequence to the learning algorithm, and then the information it has seen so far is only positive information. So I can just remove some element from it that it has not seen a positive information about so far. And then I obtain another set in CoFin that is a strict subset of the natural numbers. And if the learning algorithm wants to learn this successfully, which it has to, when it wants to learn the whole collection, then it has to fall back to a strict superset. So this is a very, like one of the very, very fundamental techniques to show separations. It's the locking sequence technique, and this already shows that monotonicity and cautiousness separate. Okay, so there are a lot of other criteria. Please do not worry, I have not defined most of them. I only talked about conservativeness on the bottom right, which implies first the strong version of non-U-shapedness, then the semantic version of non-U-shapedness. And also on the left, you can see strong monotonicity and monotonicity. And cautiousness is a bit a bit below the capital T on the top, which means that we require learning success, but we do not require any additional properties of the learning process, like, for example, non-U-shapedness. The arrows you see in the picture are implications. So these properties imply each other. I talked about this a bit for conservativeness and non-U-shapedness, for example, and also for strong monotonicity and monotonicity. And questions that are often investigated are of the form, for some model, we talked about this explanatory informant learning model, which criteria are separated or equivalent. Okay, so what was known already is that cautiousness is restrictive in this model. And also it was known that strong monotonicity separates from monotonicity, and also that monotonicity is a restriction. And we observed also that also the other way around. So cautiousness and monotonicity are really incomparable. And we showed what I mentioned briefly earlier, that conservativeness is not a restriction. And the proof actually also shows that strong decisiveness is not a restriction, with which this diagram collapses to what you see here. So the outlined areas are collections of these learning, additional learning requirements that are of equal learning power. Okay, and one property of these additional requirements that comes in handy for the lemmas that I mentioned earlier is so-called delayability. And delayability says nothing but that in the picture you saw earlier with the developing learning process with time, that the additional property is not influenced if I delay the hypothesis. So in the sense that I have an unbounded and a non-decreasing function called a simulating function S, and I have, for example, different presentations that the simulating function translates the one presentation into the other, in the sense that at time t, this presentation I prime has at least as much information available as the other information stream, capital I, has at the point a simulating function s of t. And this holds for the positive information, so the positively labeled, and the negative information, the negatively labeled information. And also, there are two learning algorithms, M and M prime. And the one bases its hypothesis on I prime, is the same one as the other learning algorithm would output on the data stream I translated with this simulating function. And if I have these properties, that seems quite technical, but you can, for example, think of it like M prime, that for example you delay every output by one, or you output like you only use the first half of the data to output your hypothesis. And then it's like very easy to see that that most of the requirements carry over, or basically all that you have seen on the previous slide in this map. They are all delayable, so they are not influenced. But but there is one criterion that is not delayable, and this is consistency. What we showed is, we showed for all these criteria that you saw on the map in one lemma that we can assume the canonical presentation. So this is what I mentioned earlier, comes in handy when showing that conservativeness is not restrictive. And on the other hand side, for consistency, we also observed that indeed that it is not the case. So there is a language class that I wrote down here. Capital H is the halting problem, that is learnable from canonical presentation, but is not learnable in general from every adversarial presentation. And so this argument relies on this is a diagonalization argument, just as the following very easy observation, namely that consistency on the successfully learned languages does not imply consistency in general on every possible presentation. So this very easy collection of languages, namely the natural numbers and the halting problem, can be learned by a learner that is consistent on these two languages, so on every presentation of them, but is not consistent everywhere. And the idea is very simple, namely you just, if there was a learner that would be consistent everywhere, then the halting problem would be decidable. Okay, and we also showed that, which we also used to prove that conservativeness is not restrictive, that we can assume the learning algorithm to always output a hypothesis. And this also again holds for the whole collection of these delayable learning success criteria. And the idea is again to define a suitable simulating function, namely by only taking into account the amount of data seen so far on which the algorithm has converged. And this will work. Okay, so now I showed you already two techniques to show separations. The one was locking sequences, the other one was some kind of diagonalization in the sense of contradicting the undecidability of the halting problem. And another very important tool that is used in proofs is the so-called operator recursion theorem. There are different versions of it. The one I'm citing here is a strictly increasing version, and it says that for a computable operator, one can find like a strictly increasing computable function, which is such that this function translates between what the computable operator does with functions and how this can be enumerated. Yeah, so in the number of the program that results basically. And in the applications of this operator recursion theorem, the theta, the capital theta, and also the h are most of the time implicit. But I wanted to state it here once so that you can maybe get a better idea of what happens in the very sketchy proof that I want to talk about. Namely, we also showed that again. So just a reminder. So we showed that that for the canonical presentation, for every delayable learning success criterion, it is not a restriction to only look at this very nice kind of presentation to cover all adversarial presentations. And this fails for the undelayable criterion of consistency. And we also showed that for all delayable criteria, totality is not a restriction. And now I want to give a vague idea of that why or this is not the case again for consistency. Okay, and what one does is one looks at a learning algorithm, one specific one that first outputs some initial hypothesis for the empty set, and afterwards always asks the data stream it sees which function to run, and also encodes the input as the argument. And then the collection of languages that I claim is not consistently learnable by a total learner from Informant is then the collection of all decidable languages that is consistently learnable by this learner. And now this is not the complete definition because it doesn't fit on a slide, but my goal is more to give an idea of how the operator recursion theorem is applied. And what is happening here is that at the same time one defines data streams A and B, and one defines the small e, an index for a recursively enumerable set, and a small set, which is an index for a partially computable function in this var-phi indexing of partially computable functions. And what happens now, or the magic behind this recursion theorem, is that it makes it possible to define at the same time these A and B data streams, which in the form of these sigma i's define a representation or an information stream that suits, or that is a data stream that that has this WE, so this recursively enumerable set, as its content or the information. And on the same side, this phi set will witness the decidability of this language. And now A and B are defined in such a way that one can prove that this cannot be learned consistently. So if the learner was total, then it is inconsistent. And this is this is possible because A and B and E and Z are depending on each other. So they all build the small h in the operator recursion theorem, and this whole case distinction that is not complete is basically stands for the computable operator. Okay, so we were all collecting all the ingredients for this proof, namely showing that conservativeness is not restrictive, and now this learning algorithm that we construct from the old one. So we assume we have a learning algorithm M that is successful on the collection of languages, and we want to show that there is another one that learns at least this collection of languages and additionally acts conservatively. And we do this by saying that this new learning algorithm only changes its mind if M did, so the old learner did, since the last mind change of M prime. And also we can see some justification for the mind change because we want it to be conservative. And as we cannot look arbitrarily much ahead, we restrict how far we look ahead by really very much thinning out the guesses, the original guesses of M. And yeah, so on the one hand side, we will only do a mind change if we have a justification, and on the other hand side, we will also thin out our hypothesis to make sure that the justification comes at the right time, to make sure we do not miss the important mind changes. Yeah, so this formally looks like this. I will not go through this in all detail, but this is like a positive result, and I also wanted to show you how a complex simulation argument looks like. So one would, yeah, one looks like in this script X with index sigma and yeah, up to the T from D, we collect all possible extensions of D that are still suitable, and then in these A sigma T's we extend more and more if we do not I mean, we only extend if we are sure that we only include information that we do not lead later on to justify a mind change. Okay, and to really check that this all works and that this new learning algorithm is conservative takes a bit more time and is technical, and I don't want to go into detail there here. What I want to do instead is talk about another model, or more models, because the model we looked at so far is a model for very classical machine learning algorithms for binary classification. So for example, a support vector machine, a classical one, would take into account all the data it has seen, and based on this compute its classifier, and yeah, and yeah, it's really based on all the data. So this is very important. Okay, also the classical perceptron does this. Now more recent algorithms, for example, neural networks, as I took a picture of from Wikipedia, in image processing, but also for other questions. What they do is they see the data, they observe the data, but each time, or in a mini batch format, after a certain amount of data, they update the weights. So for example, by a stochastic gradient descent, but these are details that we are not concerned with here. There's very important research on that too. What these learning algorithms do is they look at the data one by one in the extremest case, and each time they see it, they update the parameters of, for example, the weights of the neural network, and forget the old data. So the new output classifier is based on the last instantiation, or the last values of the weights, and the currently observed datum. And this is yeah, so these are the kind of machine learning algorithms that we try to model as well. And there are two approaches I want to talk about. The one approach is called iterative learning, introduced for example by Wiehagen in '75, and the learning algorithm is iterative if its output is only depending on the last classifier output and on the last input. And in contrast, bounded memory states learners, which were introduced in 2007, are very similar, but there is a slight difference, namely the new output hypothesis also depends on the last input, And it also depends on the last state that the algorithm is in, that is based on the previous data. Okay, so once we really use the classifier itself, and once we kind of use states, which you can, for example, think of as parameters of the algorithm. Okay, so in the BMS star definition, only a finite number of states is allowed in the limit, which kind of corresponds to our definition of learning success. What is very easy to observe is that every iteratively learnable collection of languages is also learnable by a BMS star learner when we use the hypothesis as states. What is not as obvious, but also nice to see, is that one can, from a BMS star learning algorithm that is successful, one can also gain an iterative learning algorithm that is successful. And this can be done by encoding the translation diagram into the hypothesis. But this is, yeah, I mean, the idea, I would like to give you the idea. The idea is that, this BMS star algorithm operates depending on the states and on the last input. So you can think of it like, yeah, like an automaton, or like a maybe Markov decision process. And whenever you're in some state and you see some datum, you know where to go. And during the learning process, you started in your initial state, and then you move around in this translation diagram. And now you store the part that you have already observed in your hypothesis of the iterative learner, so that you can make sure that you will yeah, always that you will always go back, for example, to states that or that you will not, so you can make sure that you will not loop by always immediately going back to the last new state that you have seen. And this, yeah, this is also something you have to think about. Okay, so the details are a bit technical, but the idea is roughly that you encode the visited diagram and also the information you need to make sure that you can always work back to the last state you've seen. Okay, so we looked at also at learning in these two memory restricted settings, and other people did that before us. And in '92, it was already observed that, again, these monotonicity criteria separate and are also restrictive. And in 2007, Jane Lange and Zillis observed that conservativeness is a restriction. So in contrast to the setting we looked at earlier, where all information is available, now in this setting, this is restrictive, but it was not clear and still is not settled where exactly the separation happens. And what we found out is, on the one hand side, which is very easy to see, that cautiousness is restrictive, and on the other hand side, that there is a separation already between strong non-U-shapedness and no restriction. And this is again a separation argument with an operator recursion theorem. So what we want to show is that there is a concept class that is learnable by an iterative learner from informants, or from binary labeled data streams, but not in a strongly non-U-shaped way, so that it is necessary to allow this behavior of deviating from a correct hypothesis. Yeah, so first one defines a specific data-driven learner. You have seen earlier an example for a specific learner that was tailored for the proof when we talked about totality and consistency. And then one again, with the magic of this operator recursion theorem, defines these data streams that refer to one another, and also hypotheses E0 and E1 and E2. There are infinitely many, or countably many E1 and E2. and they are defined such that that WE0 contains the positive mind change data from A, and WE1 and WE2 additionally contain data of B, and they are sometimes equal, but not always, and are defined in such a way that not both of these sets can be learned strongly non-U-shapedly. So this is a proof of multiple pages, but this is the basic idea. And yeah, and in the operator is represented by algorithms given, and these A, B, E0, E1, E2, they are stand for the H for the function that exists. Okay, so we first saw this map of full batch or full information learning from binary label data, and yeah, for learning from text. Also for iterative learning, this map was known. So there have been very impressive results to achieve that. And what we also observed is that for the BMS star algorithms, so the algorithms based on the states, this looks the same. So one of the most important results I mentioned, namely showing that that for without any restrictions, it was already known, but we showed also for all the semantic delayable restrictions that these two models actually are equally powerful. So for all but SNU, SDEC, and conservativeness, indeed, we can use the results that have been shown for iterative learning from text. And I have not said what text learning is. Text learning is the setting where you learn from solely positive information. So in contrast to seeing more and more data points that are labeled positively or negatively, you only receive a stream of the positively labeled data streams and possibly pause symbols. And this has intensively been investigated as well. And we contributed to this by observing that for the state-driven learners with restricted memory, we obtain the same map. And we also showed that the two models are yield the same map, but they are not the same. So we showed that for strong non-U-shapedness, they are different. Okay, so text, so text learning and informant learning can be compared, and there are various results. I only want to mention some regarding the memory restricted models. And it has been known that, that for example, this collection of all natural numbers but zero and all finite sets containing zero, this can be learned from text. It can be learned iteratively from informant, but it cannot be learned iteratively from text. And also the co-finite sets that we saw earlier are interesting because they can be learned iteratively from informant, but not from text. Okay, and we showed that there are also collections of languages that separate the other way around, so that are learnable from text in the sense of eventually being correct, and but cannot be learned from iteratively from informant. Okay, and this collection is uses the idea from the first bullet of the enumeration, but now with an additional dimension in which it is infinitely many points, the one part, and on the others, the other part. Okay, so this was already a lot of information. What I, in the end, want to show you is some algorithm that is geometric, and also the proofs are geometric. Maybe before I show you how it works, I want to say that that we were also wondering how one can encode the set of half spaces, and whether one can analyze the learnability of half spaces for these memory restricted or memory efficient learning algorithms. So we discussed in the very beginning of the presentation with this Occam's razor strategy, just that by just sticking to the best or easiest suitable half space that fits the data, that this is already a successful strategy. And this works indeed not only for this collection of half spaces, but for every collection of languages that is uniformly decidable. So has a nice way to, or has a nice underlying structure that helps to do this kind of learning strategy. But for memory restricted learners that might not work, because we cannot check whether our current, whether the hypothesis suits all data, because we don't have access to all data. We only have access to the last datum and some aggregated form of the previous data. Okay, and we came up, so we showed a positive result, so it is learnable, and the idea of the algorithm is as follows. So the learning algorithm receives data points and it waits until it sees 4 data points, 2 of them labeled positively, 2 of them labeled negatively, which have additional properties, namely the 2 line segments are of minimal distance with respect to the angle, and also yeah, they overlap, so the minimal distance is realized between them. And then one might see more data that is consistent with this hypothesis. So this is just ignored. And then one might see data that is not consistent. And then this, yeah, and this so-called, or this, I mean, the data state stands for a hypothesis and also is kind of information that tells you what data made you think that it is this hypothesis. Okay, so there is another data point, and you collect more and more. I mean, right now you're in a collect mode, so you will collect more and more until you again reach this kind of locking state. And again, you have the minimal distance realized between the line segments, and then this is not consistent, so you will collect more and more, and this goes on, and finally you will have reached your correct half space that suits all the data, and that you will also see in the future. And yeah, and what we additionally later on looked at also is finding out whether for other memory restricted models of learning, this collection of half spaces is still learnable, and this is also something that we're still working on. And yes, so thank you very much for your attention, and I hope that you gain some nice insights.
Thank you very much for a very nice talk. Do we have any questions? Anyone? Just unmute yourself. You have any? So I have a very maybe general question. So you talked about differences between the results for learning from both the positive and negative information and only from the positive information. Is there anything like, well, differences also in techniques that are used? Can you maybe, so you mentioned several times that here you use this operator recursion thing as one of the main techniques to prove this kind of results for learning from Informant. What about learning from text? And also the other way around, are there any results that you get like for free, like that are transferred from learning from text to learning from Informant?
so the operator recursion theorem is a technique. So thank you very much for the question. This is very interesting. I'm not sure that I thought it through completely. So first of all, the operator recursion theorem is a technique that is like traditionally used for learning from text. So we kind of, we're thinking about how this is also useful for learning from Informant. And some proofs that we came up with are very much relying on the ideas when learning from text, but really incorporating the negative information appropriately. And on the other hand, when learning from Informant, some ideas that for learning from text, for example, are very complicated, become easy. And on the other hand side, there are also results that when learning from text, they are very complicated and complex, but they cannot at all be transferred to learning from Informant. So my favorite example, because I thought about it a lot, is this non-U-shaped learning for the memory restricted setting. It's a very nice proof to show that this is not restrictive for when learning from texts. And this proof does not work at all for learning from Informant. So I would say for the simulation arguments, learning from text arguments do not always transfer. So this is not at all trivial. Yeah. I'm not sure I answered all your questions, so maybe just ask again.
Thanks. Okay, thanks a lot. There's no other questions, or maybe no. Okay, so thanks again.
Yes, thank you very much
for taking your time.
For your time.
Just such late hour.
But yeah, it was quite convenient, and I hope that I'm glad that so many people joined. So thank you very much.
Yeah, so let me stop the recording.